get assembly code for a new machine specification that specification is going to come online. So you get assembly code. This is just like a standard way that you work with any program these days, right? Now comes the new stuff. In this pre-processing phase, which in the case of Bitcoin could be set up by, the Bitcoin, I don't know what the central authorities are, but for any computation that is deemed important enough, someone will do this pre-processing phase. And in this pre-processing phase, you take the assembly code, you take a bound on the running time of the program, you take some auxiliary randomness used for cryptographic purposes, you throw it into a cryptographic engine, which is the main thing in our work, and out come two things. One is the prover's key, and the other is the verifier's key. The prover's key is pretty long, it's as long as the computation, but the verifier key is really, really short. So now the prover gets the prover key, and it can be posted, for anyone to use. And the verifier with the verifier key. So for instance, for the prover key, if this is proving all transactions or the last block is consistent, this will probably go to the nodes, and we'll just have it there always to use when we're signing the base work. And the verifier key, which is very long, will also be posted, and anyone can just download it onto their mobile app. This would just be part of the client sitting there. And the prover will get the input, could be the block, the latest block of the blockchain, all of the blockchain, and the prover's key, and will do a computation which essentially runs through the execution of the C program and signs it. So out will come an output, which should always come out, and a signature. The signature reveals nothing but for the correctness of the output of the program. So even if a single bit in the execution is by mistake or maliciously changed, the signature won't match up. And Alice will have a very easy task of verifying this thing. That's phase one. Phase two is even sweeter. The pre-processing is really just compiling the program into this new assembly code that we have. And this can be done by anyone. It can be done by Alice because it's so easy, by Bob, or by the system. Now the prover will execute it, and will send again the output and the signature, which Alice will verify at very minimal cost. So this is really as lean, as asymptotically good that you can hope for. And this hopefully will be by the end of the summer. So just a little bit of numbers again in the context of Bitcoin, and I just should say that these numbers are going down all the time. So this is not the end point, this is the start point. Our main measure of efficiency is there are constraints generated. Basically, the prover just has to prove that a whole lot of constraints all match up. Every step of the computation was okay, and in a cryptographic way, then compress it into a signature. Okay? So the main measure of efficiency is going to be the number of constraints. And right now, we can just verifying a single step of our abstract virtual machine, which say takes 16 registers with 32 bits. So it's a pretty powerful kind of framework. You have quite a lot of registers there. And I should mention that you, of course, have random access memory. So you have a whole lot of memory out there that can run a lot of things inside the memory. That's going to cost you about 1,500 constraints per one machine cycle. And we did a back-of-the-envelope calculation showing that if you want to verify a single SHA-256, it's going to take you currently around 20K constraints. And we're already playing with systems that handle between something like around 4 million constraints, and we're going to boost it up pretty soon to 30 million constraints. And our only limitation is the randomness that we have on the machines that that are currently available to us. We haven't bought any specific hardware to deal with it, but this is completely scalable. We just need more memory to fit the whole thing inside. So the bottom line would be that if you want to have computational integrity and privacy for some simple C programs that will also include roughly 1,000 SHA-256, then this is something that within a few weeks we should be able to do. So looking ahead, suppose Bitcoin likes this project, and I hope they do, I think they should. Suppose, bear with me for a minute, that at some point in the future, fourth layer script is about to be replaced with C, which which could be a good idea for a lot of reasons. And even if not, you could just have this as something that builds upon the basic Bitcoin protocol. Then you could use our system to guarantee privacy and integrity, and there's a whole range of things that you could do with that. You could get untraceable proofs of payments and proofs of ownerships. You could get untraceable auditing, again, verifying all kinds of things about your history for tax purposes or whatever it is without revealing any information about the actual coins that you own and so on. This could also be good for receipts for merchants to have tangible proofs that someone paid something without revealing any information about them. You could do things like exchanges and contingent payments and future contracts in a much simpler way. Again, because you could just be writing C code. And here I want to thank Greg Maxwell for raising this idea of contingent payments to use zero knowledge and computational integrity and privacy for it. Greg, there you go. Thanks. Okay, we should chat afterwards. And you can also boost anonymity by, so you all saw that there's this really spectacular work about the zero-coin protocol, and using our system you could do similar things of anonymizing, taking a lot of coins into a big pool and distributing them into a way that you never know which coin came from which coin here went to which address there. You could do it in a more seamless way by writing proper C code that basically adds up the coins, proves that it knows 1,000 addresses. Here are the addresses. They went pooled into one place and then they got distributed, and all you learn is that everything matches up, but you don't know which input goes to which output. Okay, so that's another thing you can do. So if you want to learn more, first of all, on Tuesday, 2 days from now, 4:30, I'm giving at Stanford Security Seminar, I'm giving a talk that will be a little bit more technical, a little bit more about how we do theory. You could also watch my previous talk. I'll put these slides that will have the hyperlinks into this talk that I gave at Stanford, again, with pretty much the same ideas, going a little bit more under the hood. Also, you're welcome, again, just all of these conferences happen to be taking place very close by. June 3rd, that's like in a week and a half, there's going to be a presentation of our work at one of the main conferences on theoretical computer science called SCIP.